Okay, so here the nuclear magnetic resonance spectroscopy. Generally, it is an absorption spectroscopy, and as you know that, right? So the spectra it is absorption spectra and emission spectra. They are depending on the then we have the two types here with the absorption spectroscopy and the emission spectroscopy. Yeah. So absorption where they absorbs the energy. Okay, they absorb the energy, yeah? And in the emission spectra, where they will evaluate the energy, like fluorescence, fluorometry, okay, fluorescence, phosphorescence. So you can observe in the Jablonski diagram. Okay, so you can see the fluorescence and phosphorescence here. So where the transition of the electrons from the higher energy level, ground state to the higher energy level here. Okay, and that is a fluorescence and phosphorescence here. So and absorption spectra where they will absorb energy. Emission spectra they will evaluate the energy here. Okay, so this is the difference of the absorption and the emission spectra. And one of the example under the absorption spectroscopy. Okay, so in this NMR spectroscopy, so depending on the nuclear, right? Depending on the nuclei, here the NMR nothing but nuclear magnetic resonance, and depending on the nuclei, so we have the various types of spectra. For example, here the nuclear, we have the H1 NMR spectroscopy. If the nuclei is carbon, then it is C13 spectroscopy. If the nuclei is fluorine, it is F19 spectroscopy. If the nuclei is nitrogen, N15. So depending on that the nuclei, we are going to classify all these types of spectroscopies here. And basically, we have the H1 NMR spectra and C13 spectra, very vast variety of applications here. Because in the organic chemistry, where the organic compounds are the composition, the major composition of organic compound is a carbon and hydrogen. That's we call the hydrocarbons here, isn't it? So hydrocarbons, like where the carbon and the hydrogen is a major composition here. So that's why where most of the atoms elements present in that particular organic molecules or the compound is composition is carbon and hydrogen. That's why these two spectra in the NMR spectra, okay, besides all the spectra, like besides all the what is it, P31 spectra, F19 spectra, N15 NMR spectra, where the C13 spectra and H1 NMR spectra, these two spectra plays very important role in the prediction of the structure, in the structural elucidation of the organic compounds here. You can take natural products or any organic products or the heterocyclic compounds. Okay, so the hydrocarbons you can take. So to analyze a compound or to predict the structure or to interpret the structure of that particular compound. So we have these two spectra is having more applications and they are playing very important role. And that's why we call these are the very key spectra in the qualitative analysis here. You know that so this spectroscopic analysis comes under qualitative analysis, isn't it? Basically, the analysis two types like qualitative analysis and quantitative analysis, isn't it? So where this instrumental methods or the spectral methods comes under qualitative analysis. And by this spectroscopy, you can be able to identify or you can be able to means find out the number of protons present in the particular compound and the nature of proton, whether it is attached to the primary carbon or the secondary carbon. So the linkage of that particular the connectivity, you can say the connectivity of the molecule you will be known by this H1 NMR spectra and by C13 spectra. So the number of carbons and the nature of carbon also, like primary carbon, secondary carbon, or the tertiary carbon. So these applications can be done by your C13 spectra and H1NMR spectra here. Okay, so these spectra having variety of applications, right? In order to find out the structure of your compound. In the NMR spectra, if you have NMR spectra here, so there are resonance condition, right? So the resonance condition is very key stage in the NMR spectra here. So generally, what is resonance generally? So here the resonance nothing but the matching of frequency is the resonance. Okay, the matching of frequency is the resonance here. So basically, the compound when they are in the okay in a compound, so where all the electrons in the ground state is in the random manner here. Okay, they will arrange or they will oriented in the random manner. Okay, so it is disorder generally called random in the sense all the electrons are in the disorder nature here. And when we applied the right that particular EMR, when we apply the EMR or when we apply the energy here, right? So then all the means some of the electrons will be oriented towards up means oriented in the upwards direction, and some will be oriented in the downward orientation. Okay, and some will be occupied at the right lower ground state level here, and some will be gets promoted in the higher energy level, and they will arrange in a systematic manner. So the disorder becomes order here, right? The disorderness will be removed when we apply the energy, right? So this is the this generally this condition is called the resonance. Okay, matching of the frequency called the resonance here. So all the electrons comes in the resonance and they will get promoted and occupies a higher energy level here, right? And we see you can see this diagram here where this magnetic field, right? So in the magnetic field is absent. Okay, magnetic field is absent, so you can see the disorderness in this particular electrons here. And when the magnetic field is present, when we apply the magnetic field, right? So under applied magnetic field, so you can get promotion of the electrons here. So they will find the higher energy level with the different spins. You know that the electrons are having two spins like okay, plus half and minus half quantum number. Isn't it? Plus half and minus half here. Some is oriented in the upward direction where the spin quantum number is taken as a plus half here, and some will be oriented in the anti-aligned direction. Aligned direction whose quantum S is okay, spin quantum number is plus half here, and some electrons are oriented in the opposite direction or the anti-aligned direction whose quantum number is taken as a minus half here. So in this way, we'll see the occupying of the electrons in various stages like the alpha level and the beta level here. Alpha level, beta level is the higher energy level. So the kind of phenomena is observed during that resonance. Okay, and we'll analyze how much energy is required to promote the electron from lower energy level to the higher energy level. So that is a we will have that signals. Okay, so that signal will be appears according to the energy absorption and intensity also we'll see. Okay. Instrumentation, we have the instrument and 120 megahertz instruments. That is the capacity of that instrument here. And if you see the instrumentation block diagram here, so generally we have the okay, so where that sample is located, the sample holder is present in between the two magnets, like magnet 1 and magnet 2 here. And we have the sample holder here. So when we keep the sample in this sample holder, okay, so we then apply the radio frequency here. Okay, radio absorbs a radio frequency. Okay, by absorbing that radio frequency, okay, so it is going to have some flipping here. So flipping means where that flipping is nothing but where the spin is going to inverted here. Okay, here where the plus half is converting to minus half, minus half, plus half. So that is the unsaturation is taking place. Okay, so this kind of flipping is taking place here, and then this particular what is that the phenomena takes place, and it is going to recorded in the particular device here. So the recorder device is recording that particular spectra, and finally that particular the whatever that particular observation is done, so it will be coming out as your output here, right? So that is output nothing but it is a kind of the graph here, right? So we will see the graph how that H1NMR spectra is already we have seen in the spectral problems. Yeah, okay, chapter here in the practicals, and you see that the solvents. Okay, because when you are going to record the H1NMR spectra, so your sample must be dissolved in a solvent here, and that solvent must be a suitable solvent here. Suitable solvent, nothing but in which your compound is going to dissolve properly, right? And the different solvents and their chemical shift values also in this particular table. You can see, okay, whose melting point and boiling point is given. The melting point is minus 93.8 here, and the boiling point is 55.5 degrees Celsius. Where the delta value, chemical shift value is, you will observe this acetone at 2.05, right? So in the H1NMR spectra graph, sometimes we'll observe a very small peaks here, very small peaks, okay, in that graph here. Okay, so that small peak generally that is corresponding your solvent, because your compound does not use a small peaks, right? Basically, you will get the very large peaks, means more intense peak here. But here, very less intense, very weak bands are, very weak peaks are observed in the graph, and that weak peaks are corresponding to your solvents. And where the probability for the appearance of your solvent peaks is given in this table. Like acetone is appeared at 2.05 delta chemical shift value here, and benzene is appeared, okay, at 7.16, okay, and where the chloroform where it is appears at 7.27, because you know that the chloroform is having 3 chlorines here as the factors in that factors where the electronegativity increases delta values, okay. So where the chloroform is attached with 3 chlorines, 3 more electronegative atoms are there. So obviously it's means delta value is going to increase more and more here. So it will be appears at 7.6, and dichloromethane DCM, right? So where it is appears at 5.37, plus 32 here, and DMS dimethyl sulfoxide, DMSO dimethyl sulfoxide is appears at 2.50 here. So these values, right? You need to remember these chemical shift values, because sometimes here along with that signals, right? Your compound signals, sometimes you will observe the additional signals also, and the additional signals it will be considered for the solvents here, because if you consider these additional signals for your compounds, then you will get wrong interpretation, okay. So we'll get the wrong interpretation here. So if you know the idea about the signals for a particular solvents here, the position of signal, the position of signals for the solvents, then it is easy to interpret the structure. Otherwise, you will do the misinterpretation here. Okay. For example, if you take ethyl chloride, the ethyl alcohol here, right? So ethyl alcohol, generally you get the three signals. For methyl, one signal. For CS3, you get one signal. For CS2, you get one signal. And for OH, you get the another signal. There are three signals are appeared for the ethyl alcohol here. And this, when this ethyl alcohol is dissolved in the chloroform, for example, here, or when it is dissolved in the benzene, so at range of 7.16, okay, it is in the range 1.16. So you will get a multiplate signal there, right? So because here the maximum possibility for getting the signal for the ethyl alcohol is 3 only. And in the graph, you are getting 4 signals here, right? So you will get confusion about this one. So if you have the idea that it may be the for solvent signal, then it is good. Otherwise, you will get the confusion and you will go for the wrong interpretation of this. So sometimes along with your compound signals, you will get the some additional signals also appeared in the graph here, and that is correct from your solvents here. And the probability for the absorption of or the appearance of your the signals for the solvent is in this table. See the dimethyl sulfoxide DMSO, where it is appears at 2.50, and the methyl alcohol, where it appears at 3.31 here, and pyridine it is 8.71, 7.5. So these are some the ranges here. Okay, because the pyridine it is aromatic compound having the nitrogen electronegative atom. Obviously, the means generally the aromatic compound appears in the range of 6 to 8, isn't it? 6 to 8 ppm. But due to presence of the as the nitrogen is a part of your ring system, benzene ring system, so its delta value is going to increase, and you will observe the signals in the range of 8.71, 7.55, 7.19. Okay, so these are the probability for appearance of these solvent peaks in the spectra, NMR spectra, and water it is appears at 4.63 here. So, for example, if your compound is not dry compound here, okay, sometimes what you do without drying the compound, or if any moisture is present, okay, if any moisture is present in the compound here, so then the water also giving the signal at 4.63, right? So these are the some difficulties while you are recording the H1NMR spectra. And don't misunderstand, means don't miss me. What is it? Interpret the graph by seeing the solvent, by incorporating your solvent peaks in the NMR spectra here, your compound spectra, right? So this is very important to interpret the H1NMR spectra here. And see that the compound must be dry, okay, and your compound must be pure form here. Okay, how to check the purity, how to make the purity here? So you can do the recrystallization of your compound, and then you check with the TLC here. You keep the TLC. If you are getting one spot, then your compound is pure, right? If you are not getting one spot, if you are getting two or more than two spots here, then your compound is impure, right? Some impurity is there. Then what you do again, you do the recrystallization, then you make the compounds pure. That is a process for, and only pure compound must be used for the spectral recording here, spectral analysis, right? Then the shielding. So chemical signals, the constant nothing but where that instrumental, right, frequency here. Then the chemical is important terminology where the chemical shift. In the exam for 4 marks, they will ask define the chemical shift and explain the the chemical shift ranges of the various compounds here, right? So very simple. What is the chemical shift here? So where the absorption position of the sample, right? The chemical shift nothing but the absorption position of the sample minus the absorption position of the standard. Standard nothing but our TMS, isn't it? Yeah, standard nothing but the inner compound. Generally in the H1 NMR spectra, we'll take the TMS as a standard compound here. Standard, uh, okay, standard material compound, because the TMS is TMS nothing but tetra methyl cetane here. Here, the TMS here. So four methyls are there around silicon. We are 3%. So around this silicon, there are four methyl groups, where all the four methyl groups falls in the same chemical environment here. Because of these are uh, chemically equivalent here, right? So you will get only one signal for this one here, one signal, and you will observe this EMS at zero delta value. So it won't interfere in the compound, or it won't interfere in the graph here. So we are taking this as a reference one. Okay, we are taking this EMS as a reference to record the NMR spectra here. And we can define the chemical shift is the observed position of the right sample, or the absorption position of your standard, and the operating frequency. Operating frequency means the megahertz, where whether we are recording that NMR spectra on 60 megahertz or 100 megahertz or 120 megahertz, right? This is the frequency, your instrument frequency here, and 10 power 6. So this is the formula to calculate the data or the chemical shift values here. Okay, and yes, so and you know that where this particular H1 NMR spectra scale is ranging from 0 to 20 here, right? The range of this H1 NMR scale is 0 to 20. And the C13 spectra, right? So its range is somewhat more than your H1 NMR, where the C13 spectra chemical shift values are 0 to 220 here. That is a scale range. Sometimes 250 also, right? Basically, the main, okay, the basic range is 0 to 220, and sometimes it is extended up to 250 here. And H1 NMR chemical shift range is 0 to 20 here. Okay, and here in this table where it is given, okay, chemical shift values here. So depending on the nature of proton here, okay, type of protons and the attachment of these atoms, like factors, we know that there are so many factors which is influencing the affecting the chemical shift values, like electronegativity, anisotropic effect, hydrogen bonding, steric hindrance here. Okay, and what is that? Angle strain, steric strain here. So all these are the factors which are affecting your chemical shift values. Right. So where it is given in this table, the values are put here. Yes. So here the alkane protons. Okay. So where the alkane protons, so where are CH2. Okay, that is sp3 protons here. So they will appear in the range of 0.7 to 1.3 here. Okay, and where the are CH2 proton. Here is the terminal CH3. Okay, terminal CH3 protons where it is range of the 0.7 to 1.3, and where this RCH2 protons, which is ranging in 1.2 to 1.4. So that is sp3 protons only. All these are the okay. So where it is a primary proton. Okay, so primary carbon, the proton attached with the okay. So the proton attached with this is the primary carbon proton here, where it is 0.7 to 1.3 here. And this is your secondary proton, secondary carbon proton, and this is your tertiary. Okay, so this is primary, this is secondary, this is tertiary. Okay, so your secondary proton appears in the range of 1.2 to 1.4, and tertiary protons appears in the range of 1.4 to 1.7 here. So what is happening here? So you can see the means gradually the way increasing of your delta values here. So the steric repulsion or the steric hindrance is increases the delta values here. Okay, here one factor is okay uh, acting on this one with the steric factor, right? Steric crowding factor is acting on this compound here. So primary it is sterically free, where secondary somewhat it is sterically free here, and tertiary it is sterically crowded. So with increase of steric crowding, where your delta values are going to increase. And next here is yes, here the carbonyl or CO or some here the diketone, where it is value 2.1 to 2.4 here. So here this okay, and cyclohexane proton, right? It is not aromatic generally. So cyclohexane, aliphatic only, alicyclic generally. We call alicyclic protons having 2.3 to 2.7. And any thio groups, okay, thiol is 1.0 to 4.0 something. And alcohol is 4.0 to 7.0. And here is amine proton, it is 3.4 to 5.0 something. So all these are values which is taken. And here the aromatic proton, it is 6.7 to 8.0 something. Okay. So these are the values which is roughly values we can observe the appearance of your protons here. Okay. And here is a cyclopropane. And here the aldehydic proton, it appears in the range of the 9.0. Ketone, it is appears in the range of okay 2.324 here. Okay. So here you can now we can see the factors influencing chemical shift values, and here the shielding and de-shielding mechanism here. Okay. So if you observe the scenario of these chemical shift values of various types of functional groups and various types of protons here in this table, so we will have the idea about the factors which is influencing on the chemical shift values here. Okay. So you see the secondary secondary alkyl is 1.3, and tertiary alkyl is 1.5 here, and vinylic proton it is 4.6 to 5.9, and acetylic proton is 2 to 3. So here you can observe that, right? So here from top to bottom here, okay, here the primary carbon proton, secondary alkyl proton, tertiary alkyl proton, Then the vinylic means alkene protons. Here is alkyne proton. So electronegativity of these protons is going to be from top to bottom. Like here we see 3 carbon proton here. Okay, sp3 carbon proton. Then sp2 carbon proton here. Then sp. Okay, carbon proton. So the electronegativity is more for this sp. Right, here is a electronegativity. sp is more electronegative than the sp2, and sp2 is more electronegative than sp3. Generally, with increase of electronegativity, the chemical shift value must be increases here because it is directly proportional. The electronegativity is directly proportional to your chemical shift values, right? The chemical shift values are directly proportional to the electronegativity, that is, or vice versa. So, based on this statement, we are supposed to have the more electronegativity, more delta values for the acetylenic proton. Acetylenic proton is having 2 to 3, and vinylic proton having 4.6 to 5.9, and alkane proton having 1.5, 1.8 range. So where it is the deviation, right? You can see the deviation in this order here, where vinylic proton is more and acetylenic proton is less, because the electronegativity of acetylenic proton is more here, but less delta value, right? So it is inversely proportional. And vinylic proton, where electronegativity is less and delta value is more, here also inversely proportional. So that particular principle or the rule is deviated in this case here. This deviation of this rule is due to that particular anisotropic effect. So, and what is the anisotropic effect, and how it will be impact, and what are the factors causing to reduce the delta values or to increase the delta values. So we'll see later here. We'll see some of delta values, like aromatic protons having the 6 to 8.5, and 2 here, and allylic 7 to 1.8, and aldehyde is 9 to 10, and ketone esters ethers is 3.3 to 4, and alcohol protons also the range of 3.4 to 4 here. And carboxylic acid, right, the phenolic proton is in the range of 4 to 12, and carboxylic acid is in the range of 10 to 12 here, right? So these values are very useful to analyze the spectral H1 NMR spectra, right? Remember the values, delta values here. So you cannot analyze the H1 NMR spectra, because we'll get the signal in this range here. And the values are some variable here. It is not the fixed values here. So some minus plus to minus will be there, right? And due to the attachment of that groups or the atoms here, so the value will be some fluctuation, right? Some fluctuation will be takes place here. And amino protons you can observe in the range of 1 to 5 here, right? So this is the chemical shift values of various groups. Right? Now the factors affecting the chemical shift values, and this is also very, very important. The factors affecting the chemical shift values. So first we'll see the inductive effect, and you know what is the inductive effect generally. So when that particular, right, carbon is attached with the more electronegative atom, right? So the bond electrons are attracted towards the more electronegative atom here. Okay, so that is called the means sigma bond electrons, transference of the or the migration of the sigma bond electrons towards more electronegative atom is called the inductive effect. Okay, so here if a proton is adjacent to an electronic withdrawing group, it is de-shielded. So de-shielded means more delta value. So in H1 NMR spectra, so H1 NMR graph here. This is your TMS reference one, and if you divide this graph in two parts, if you divide the H1 NMR spectra in chemical shift values here, and here is a intensity. Okay, here is a transmitted, so the absorptions, there is absorption, other intensity, percentage of intensity here. Okay, on y-axis we take the values here, and if you divide this graph or the table in two parts, like it is the right side part is called the shielded region. It is a shielded region, and upfield, called it is a upfield or shielded region, where this part is having the less delta values. It's starting from the 0 and having the less. Okay, and the part falls in the left side is de-shielded region, and downfield we call this de-shielded is another downfield here, and more delta values here, higher delta values. Okay, field or the de-shielded region is having the higher delta values. Yes, now we'll go for this discussion, where the particular, okay, attached with the electronegative atom or the electron withdrawing group, right? So it will be de-shielded, means presence of more electronegative atom or the electron withdrawing group appears in the de-shielded region, causing for the increase in the delta values here. And if it is adjacent to an electron donating group, where it is shielded, right? So electron withdrawing group increases the delta value, electron withdrawing group decreases the delta value. Here you can see some examples, like yes, silane, tetramethyl silane, TMS. Generally here the silicon, it is surrounded with the 4 methyl groups here, sorry, right? So where the methyl groups are the donating groups here. So donating groups decreases the delta value, and generally it is all the methyls falls in this particular same chemical environment, so its delta is 0. Okay, and the methyl proton, it is 0.86 here, and in the aromatic, okay, so in the aromatic benzene, right? So means attachment of benzene. So it cause for decrease in the, okay, 2.3, right? So here is where you can see the CH3X. Okay, so here is X is, for example, the X is a benzene, right? X is a benzene here. So then its value will be 2.34. Generally, the aromatic range is 6 to 8.5, right? But when this benzene is attached with CS2 group, then its value drop to 2.34. And when this CS3OH alcohol, it is 3.4. And when the fluorine, right, it value is 4.27. And chlorine, it is the increase in the 3.06, because yes, the fluorine is more electronegative, then fluorine is less electronegative, means then fluorine, then bromine. So based on that, their electronegativity, the values will be changes here. And the proton attached to carbonium ions are de-shielded, and protons attached to carbanions are shielded here. Yes. So here you can see the proton, when the protons are attached to the carbocations here. Carbonium ion nothing but carbocation here. So they are de-shielded because they are electronegative nature here. Carbocation is electron deficient one. So its value will be, delta value will be more. And when the protons are attached to the carbanion means negative charge. So it's causing for the decreased delta value. And the anisotropic effect, very, very important question here. So generally anisotropic effect, this is also one of the factor which is causing for the changes in the delta values, chemical shift values here. So the term anisotropic effect, it means is, so when the different effects in different directions here. Okay, so in a compound, okay, so when we apply the external magnetic field to that particular compound, so the produced field, okay, the produced effect, if it is distributed equally, then we call that is a isotopic effect. And the produced effect when it is distributed unequally, then we call it is a anisotropic effect here. Okay. So when it is distributed equally and when it is distributed unequally, and what type of compound are exposed to that particular anisotropic effect, and what type of compounds are not exposing to that particular anisotropic effect. So we'll see with this example here. Here you see where this particular, right? So olefinic proton, right? So here the olefinic bond, where here you see, okay. So here these two sides, here is a plus and plus, here is a minus and minus here. So this is the diamagnetic region, plus. Okay, plus is a diamagnetic region here. Okay, plus is a diamagnetic region, or we call that is a de-shielding region here, and minus is a paramagnetic region. We call that is a shielded region here, right? So if the orientation of compound, the orientation of your molecule or the compound is in the, right, the orientation of the molecules protons here, because this is your proton H1 in MR, proton in MR here. So when the proton is exposed to this, absorbs the external magnetic field, then we'll see the differences of your delta values here. So in this particular case, when the proton is falls in the diamagnetic region, so it will be experience more, right, delta values here. And when it falls in the, if any proton is falls in the paramagnetic region, so it is having the less delta values here. Okay, so in the aldehyde protons also you can see here where the in the, okay, here the aldehyde or the carbonyl, you see in the carbonyl, if it is the proton, so this proton is falls in this plus region, plus nothing but the de-shielded or the diamagnetic region. So it will be experience more delta values here. And in the minus region, you can see only the oxygen. So it's not considered. And in this particular benzene, okay, so in the benzene, where the paraprotons, okay, so in the benzene, we have the three types of protons here, where we get the three signals for this benzene. So here is a, it's R, is a, okay. So where the paraprotons are falls in the diamagnetic region. So they will have the higher delta values. And meta and ortho, okay, meta and ortho, this falls in the paramagnetic region. Okay, so they will experience less delta values. Okay. And in the acetylenic proton also, right? In the acetylenic proton, so where the orientation, okay. So here the acetylene are the olefin, alkyne, okay, alkyne. So alkyne protons. So with this particular, right? So the orientation of proton, the group is like this here. So generally, this is the okay. This is the minus region here. This is the plus region. This is a diamagnetic region. This is paramagnetic region. So your protons is under. Okay, your protons are fall in the paramagnetic region. So they will show the less delta values. This is called the anisotropic effect. And here also you can see in the some in the anions also you can see cyclopins in the anions. Okay, in the cyclic compounds, cyclic compounds, and some alpha pinene and narbornine compounds. So you can see the differences of the delta values due to the orientation or the arrangement of the protons. Okay, location of your protons. So particular orientation of these protons. So there are some will appear in the shielded region, some will be appears in the de-shielded region. Okay. And spin-spin coupling and its so the H1 NMR spectra. Generally, the H1 NMR spectra, we have it is a heteronuclear. Right? There are two types generally. So CH, yeah, and HH. Yeah. So here is a homonuclear coupling here, and this is your heteronuclear coupling. It's a heteronuclear coupling. So in the H1 NMR spectra, so we'll see the homonuclear coupling here, not heteronuclear, because the proton, right? So for example, here is proton. Here also one proton here. Proton will be coupled with this proton and this coupled with this proton. Both protons, the adjacent protons, so mutually coupled to each other. And due to this coupling, so where it is having the signals in here. Okay. We call this is the spin-spin coupling. Okay. So when the multiplicity is generated in the signal due to the mutual coupling of the protons here. Okay. Mutual coupling of the adjacent protons. And the particular line, okay, example, this thanks to yes. KR Rao, మ్యూట్లో పెట్టుకోండి. KR Rao మ్యూట్లో పెట్టుకోండి. Getting my point. KR Rao మ్యూట్లో పెట్టుకోండి. We are getting disturbance here. Here the spin coupling nothing but where okay, you see, for example, yes, here is a proton, here is a proton here, or here is a proton, here is a proton. Means the two protons are adjacently, or the two protons on the same terminal, same carbon here. Okay, so here these two protons, right, mutually coupled to each other here, right? So this proton are coupled to this proton, again this proton coupled to this one. If both are in the, means we call this is the, right, vicinal coupling. This is vicinal. This is called vicinal coupling here. Vicinal nothing but when the two protons are in the 1-2 position here, 1-2 coupling. We call the 1-2 coupling or the vicinal coupling. And when the two protons are on the same carbon here, then this proton coupled with this one and this proton coupled with this one. We call this the geminal coupling here. Right? This is geminal coupling. This is vicinal coupling. This is geminal coupling. And some allylic coupling also. It means 1-3. Here is a 1-1 coupling. Here is 1-2 coupling and 1-3 coupling. That is allylic coupling. Okay. So these are some types of coupling, spin couplings here. And generally, the spin coupling is very important topic in this spectroscopy. And so this coupling, right, spin coupling and coupling constants. So all this we discuss in the tomorrow class here. So now we are. I am going to stop here. Right? So we discuss tomorrow. The remaining part we'll discuss tomorrow here. So I'm stopping here. Okay. Good evening to all.
Here next class. Can you say everyone about physical chemistry class? Having or not?